say anything incriminating anyway. Okay, here we go. Y equals e to the x over x. Oh, as a quick little introduction, this is the homework assignment number 2, A through E, for all of your viewing pleasure, right here. Okay. Now, when you're doing these, you want to always start with infinity and negative infinity. That should be just hands down, doesn't matter what graph you're doing, that's how you start. Good enough? Oh. Now, when you put infinity in this, you have e to the infinity over infinity squared, right? Which would, in fact, mean that you have infinity over infinity. Couple options here. One, recognize that e to the x is always the strongest function, is going to obviously outwin this lovely x squared. Second option is to do L'Hopital's. L'Hopital's would indicate that I would do e to the x, and I do the derivative of the bottom. We put infinity in here, you get infinity over infinity. So you do L'Hopital's again. And so what do you end up with that? E to the x over 2. And so long and short of it, you could have just figured out that e to the x was the strongest function, and regardless, this would be infinity. What about negative infinity? It also would have been infinity, right? Oh, wait, no, it wouldn't. I lied. I lied. E to the negative infinity would mean what? What would that do? So we could do 0 over 0, or rather think of it as you have 1 over e to the infinity. Right. Regardless, you're going to end up with, it does make a difference. Regardless, you have 1 over infinity and you get 0. The 0 over infinity would have saved you a bunch of time. Okay, that's all. So it is 0. All right, are we good with those? Now, to move forward in this particular graph, what helps in this case, and we did this one actually on the boards on Monday, or at least one that was very similar to this. One of the things you want to recognize is the fact that you have an x squared in the denominator, or you actually have a denominator, which means there is a value that's going to make this undefined. And what is that value? So you want to evaluate, and I'll change colors here, to 0 plus 0 minus. That is a value you want to actually look at. When you plug 0 in to the top, you have e to the 0. So that would be 1, right? And when you plug 0 into the denominator, when you square it, it's going to become 0 plus, regardless of whether it's 0 plus or 0 minus. Are you still with me? So these would be both infinity. Is everybody good? Now, as you start to grasp this, and honestly, if I was doing this for a particular CLEP question, the first thing I would do is I would start with my graph right now, and I would say, all right, I got the fact that I got an asymptote at 0, and so as I start to graph these, 0 plus goes to infinity, and infinity goes to infinity. And there's where the question mark starts, because something's going on between those two arrows. Now, on this side, it's not as difficult. You following that? Because you have it going to infinity, and it's approaching 0. So that part, all right, we've got that side pretty well nailed down, but something's going on here to the right, and that's where the derivative part comes in, because we've got to be able to figure out, is there a max or a min? Obvious, I hope anyway, that there is a minimum. So we should be able to do the derivative of this. So when I'm doing the derivative of y equals e to the x over x squared, there are a couple options. One would be quotient rule, right? So you could actually do low d high minus high d low. Low, derivative of high, minus high, times the derivative of low, all over low squared. And so whenever you're dealing with e to the x, just to kind of shorten up my explanation time here, you want to factor out that e to the x, truth be told. It's going to save you a lot of time. Also, another thing I noticed is that there's an x in common. Do you follow that? And so I would have an x out in front, and the bottom would, or the rest of that would be x minus 2. And the denominator is still x to the 4th. This saves me because when I want to know when the first derivative equals 0, in other words, define the max and the min, this cuts out a little bit because I can say, oh, well, it equals 0 when x is 0 from this guy out here. e to the x will never equal 0, so that's not going to help me give me some value here, right? And we would have it 2. So you're like, okay, 0 and 2. What's the problem with that? 0 is not going to do anything for it, right? Because it's going to make that thing undefined. So 0's out. So all I really needed to do was look at 2. And wherever you tack that on into your chart, it doesn't really matter. I plug 2 in here, I'd have e squared over 4. And so that means that this lovely thing dips down, hits at 2, and I'm just going to label this as e squared over 4. All I know is it falls in the first quadrant. I know that it doesn't dip down below that. I also know that there can't be a bunch of ways in between those two. It only is one minimum. Good? Understanding? Okay. All right, y equals the cube root of x. Again, infinity, negative infinity. Cube root of infinity is still infinity, and the cube root, can we do the cube root of a negative infinity? Can we do the cube root of a negative number? Let's just take a negative number. Can we do the cube root of negative 8? Yes, you can. It just stays with its sign. Okay? So that gets me there. Is there anything that makes this undefined? No, there's no denominator. That should be a quick and easy question for you. So we're good there? So the next piece, of course, is to do the derivative. So I'm going to rewrite this as x to the 1/3, so that when I do the derivative, it's a little bit easier to deal with. The derivative, of course, would mean this would drop down in front, and we'd go down by 1. Any questions so far? Good? Okie dokie. Now, as you look at this question, I would even rewrite this to see, okay, when does that equal 0? What makes a fraction equal to 0? That's the question you need to ask yourself. Because if you can't answer that, we're in trouble. Only when the top equals 0. Is the top ever going to equal 0 here? What that means to you is there's no max or min. Something's going on here, and there's no max or min. So that's what that says. And you're like, okay, so I'm still lost. The only other clue then is our second derivative. You're like, that's not going to help me. Your second derivative tells us the concavity, which means I'm going to know whether, see, I can tell that something's going on here that's going to make this thing go up like this, or it goes like this. I mean, that's really the bottom line. It could be a straight line. It could be a straight line. So that would be another question. Is there any concavity at all? The way you would determine that, of course, is still by the second derivative. That's exactly right. When you do the second derivative too, you would find out, right? You would find out in the second derivative that, wait a minute, there actually is a change in concavity of this thing, okay? Also, to be a line, right, to be an actual line would mean that when we do the derivative, I mean, this obviously is not a line, right, because it's a cubic. It's not a cube root, excuse me. So it obviously it's not a line. Okay, all that to simply say, there's another hint about this, that you wouldn't even have had to do the second derivative to see this. If you look at this concavity, you're saying to yourself, okay, I don't even think about the second derivative. If this, okay, if we're saying that the first derivative there's no place that it's going to equal 0, nowhere. This slope would have to be 0. That would have to kind of come in flat. There would have to be an instant at which that would be changing. And so, honestly, right here, the fact that it doesn't have a derivative means this is the one that it is, because that's a vertical line. And that means the slope there is undefined, or there's no slope. So believe it or not, this does tell you all the information, but maybe you just didn't know that. So just to kind of extend this and show you the second derivative would mean that we would drop that down in front, and we'd continue to go down by 1, right? And again, it's not that necessarily we're looking for an inflection point, we're also looking to see for concavity. I'm just going to write this all out. And what concavity basically means is what's going to make this positive and what's going to make it negative. So, because if you think about this, what kinds of numbers, maybe rephrase this, do you see that this is a -2 on top? If I want this positive, that's what this means, the denominator then would have to be negative. So what numbers, if I put a negative number in here, will it be negative? Negative to the 5th power cube stays negative. Do you follow that? So when x's are negative, it's concave up. And when you do this one, for the same reason, right? We've got negative. We want it to stay negative. That means I need this to be positive, which means, yes, your x's are positive. It is concave down. And so, boom, that's how that looks. Y equals x cubed plus 3x. Infinity and negative infinity. Infinity cubed is infinity. Negative infinity cubed is negative infinity. I'm going to just do that kind of quickly. There's nothing that makes that undefined because this isn't a fraction. So what I'm going to do right now is go right for the derivatives. Are you good with that? All right, derivative. Y prime. 3x squared plus 3. Is that equal to 0? What do I notice? Factor out that 3. All right, it doesn't really help me because we can't factor this. You can solve this though. 3 is not a root. X squared equals -1. X equals plus or minus I. Okay, what does that mean? There's no derivative. That's basically what it means. It's imaginary. It's gone. No solution there. Okay? So let's do another one. We obviously can still graph. There's still something going on here. There is values here. We just got to figure out what it looks like. So now we're going to go for the second derivative, if that helps you, again, okay? For the same idea as all these other ones, with second derivative would be 6x, and you set that equal to 0. What does that mean? It means there's an inflection point at 0. It is changing in concavity. Yay. Okay, so I've got to, if you want to put 0 in, it would be 0, 0. Okay? So now if you want to think about, okay, when is this thing positive and when is it negative? Because if it's concave up or concave down, what values of x will make this positive? Positive numbers. That means for all your positive numbers, it's going to be concave up. And this is a lovely, I'm just going to save ourselves a little bit of time, looks just like that. And they're saying this is an inflection point. Okay? All right, last one. When you're doing these, first thing that stands out to me, yes, you can do infinity and the negative infinity, but the first thing I personally would do when I look at this one is see, can it simplify? Because if I can make this look a little bit nicer, I will. And so when I factor this, I'm kind of hoping, you guys are well versed enough in factoring, that you recognize that the x minus 1s are going to cancel out. What that says to me is that this is the same graph, same, except one little detail. What's the detail? There is a hole at 1. We have to still accommodate for the fact that this has x minus 1 in the denominator, and 1 would make it undefined. So all that I really had to do was be able to graph this line with a y-intercept of -3, an x-intercept of 3, and all is great except where 1 is. We're going to put a circle. Here. Just like that. And that is it.